Hello, I'm Shaumik, and I'll be presenting our work, ReconResNet, Regularized Residual Learning for MR image reconstruction of undersampled Cartesian and Radial data. Magnetic resonance imaging, or MRI, is a non-ionizing radiation imaging modality which provides multi-contrast tissue properties and can well differentiate between fat, water, muscle, and other soft tissues. One big drawback of MRI is the long scan time, making it difficult to be used during interventions. Reducing the scan time can not only help in the interventional usage, but can also improve patient compliance, reduce motion artifacts, and increase patient throughput. MRI is not directly acquired in the image space, but in the frequency space, which is called the K-space. The inverse Fourier transform is applied on the K-space to obtain the final image. By ignoring parts of the data, the scan time can be reduced, but might result in artifacts due to the violation of Nyquist criterion. This work focuses on improving such images with undersampling artifacts. Here we have proposed a ResNet-based model named ReconResNet, where the undersampled image with artifacts is supplied as input to the network, and the fully sampled image is compared with the output of the network for calculating the loss. Inside the model, the input is downsampled twice, and then 14 residual blocks are applied. Each block consists of a pair of convolution and instance normalization layers, separated by a parameterized ReLU, and a spatial dropout with a probability of 0.2. After the residual blocks, the image is again upsampled 2 times to obtain the original image size back. And finally, a fully connected convolution layer is applied to obtain the final output. The final output of the method does not totally depend on the network. While training, only the ReconResNet is used, but during inference, the whole framework is used. This proposed NCC1071 framework for undersampled MRI reconstruction uses this ReconResNet as its backbone. The originally acquired data present in the undersampled K-space is replaced in the network's output to obtain the final output of the framework. This is called the data consistency step, and it is widely used during compressed sensing reconstruction of undersampled Cartesian data. Here we are also proposing a similar method for radial undersampling. Now let's have a closer look at the workflows. First, let's have a look at the radial workflow. Adjoint NUFT using PyNUFT is applied on the undersampled K-space to obtain the undersampled image. This undersampled image is then supplied to the network as input. And once the network provides its output, forward transform is applied to obtain the output K-space. Then the originally acquired data points from the undersampled K-space is replaced in this output K-space to obtain the final K-space. And then adjoint NUFT is applied on this final K-space to obtain the final image output of the framework. Now let's have a look at the Cartesian workflow, which is quite similar to the radial one. Inverse first Fourier transform is applied on the undersampled K-space to obtain the undersampled image, which goes as input to the network. Once the network provides its output, fast Fourier transform is applied to obtain the output K-space. The originally acquired K-space lines from the undersampled K-space is then replaced in this output K-space to obtain the final K-space. On top of that, inverse fast Fourier transform is applied to obtain the final image, which is the final output of the NCC1071 framework. To evaluate this approach, 2 different datasets were used, OSS1 and ICSI. As these datasets only contain reconstructed images, the single-channel raw data was artificially created by applying fast Fourier transform. 150 subjects were used in the OSS training set and 200 subjects for ICSI. 100 subjects each were used for both test sets. Undersampled data was created artificially. For Cartesian sampling, variable density 1D and 2D sampling pattern and uniform 4-step grappa-like pattern were used with different acceleration factors. For radial sampling, 30 and 60 spokes golden angle sampling was performed using PyNUFT. Here is an example result for different undersampling patterns. It can be observed that the framework managed to reconstruct even heavily corrupted images with high similarity with the ground truth. Now let's have a look at the quantitative results. The first figure shows different levels of Cartesian sampling, where we can see that the framework could handle all except one undersamplings really well, even for 2D variable density sampling of 5% of the K-space, which can result in an acceleration factor of 20. In the second figure, the results of NCC1071 for different Cartesian and radial undersamplings are compared against L1 wavelet regularized compressed sensing reconstruction, and performed significantly better. In the third figure, we can see the results of our model compared against UNet for 3 different sampling patterns. Here also the proposed model performed significantly better than the UNet model. Now to conclude, we saw that the proposed NCC1071 framework can work with both Cartesian and radial undersampled data for acceleration factors as high as 20 and 17 respectively, and provides results with high accuracies, while achieving statistically significant improvements over the baselines. It is to be noted that the acquisition time can be further reduced by using techniques such as parallel imaging. Given the fast inference speed of a trained network and these acceleration factors, this proposed framework can be a candidate to be used for real-time MRIs like interventional MRIs. The code of this project is available publicly on GitHub. Thank you so much for your attention, and feel free to contact me for any questions or feedback.